All right, evaluate the correlation. So again, remember RE crit is 5 e to the 5th. Okay, we need the Prandtl number, so Prandtl is nu over alpha. So we could evaluate that out, and that is 2.69. That's what this particular fluid happens to be. The Reynolds number. So the Reynolds number is now in terms of the characteristic length. The characteristic length for this, right, think of it, is it going to be X or is it going to be L? Right, it's going to be L because we're talking about the full length, right, the average over the full length of this plate. So the characteristic length here is L. So this is Reynolds in terms of L. So evaluate that. That is rho u infinity times L over mu. So this is, let's see, plug in numbers, 978 times 3 times 1, that's our length, over 4.2 times 10 to the minus 4th. And that gives us about 7 times 10 to the 6th. Okay, so that is our Reynolds number for this problem. All right, any questions on what we've done so far? Yeah?
Can you explain again why you took the Nusselt number correlation as opposed to the friction coefficient correlation?
So for this problem, I'm trying to evaluate heat transfer, right? This is asking for calculate the total heat transfer. So for the heat transfer relationship, the heat transfer coefficient is related to the Nusselt number, right? That's the non-dimensional form. The Nusselt number is sort of the non-dimensional form of the heat transfer coefficient. If we wanted like shear stress or force or something of the fluid on the plate, then we would use the friction coefficient. Okay? Yeah?
Could you explain how we knew it was force convection and how that affects what correlation we just chose?
Sure. So it's forced convection. So this is a good question. It's forced convection because if you look at what's happening here, you have these sort of magic arrows that are coming in, right? Like there's something external to the problem that is causing the fluid velocity to be non-zero. So here we're just saying this velocity is coming in at 3 meters per second. It's coming from some other source. It's a pump, it's a fan, it's something like that. But it's being imposed on this problem. If as you're solving this, as we'll see in a few lectures, we're going to do natural convection. If it doesn't give you a velocity, but it's a convection problem, that's a good sign that somehow the velocity is being generated by the system itself, right? So here it's a forced convection because something external to the problem is imposing a velocity. Other questions? Yeah.
So just trying to tie things together, like for the correlation part, like in our homework, we didn't use any of those because we wanted to use the approximate versions, right?
Right. So in the homework, I instructed you to do just an approximate model of the boundary layer because I want you to think about how boundary layer thickness relates to heat transfer and conduction through the boundary layer. When it comes to actual accurate solutions, for the most part, like we talked about last time, you're going to want to use a correlation because that's going to be a better estimate of the Nusselt number than just taking K over the boundary layer thickness. Okay? Okay, so we're this far. We have our non-dimensional values evaluated. So the next thing is you actually use the correlation. If it's E's, like you just take your Reynolds, your Prandtl, you plug them in, and you get back your value. If you don't have E's available, or you have a textbook available, or some paper where they've published a set of curves, you kind of have to interpret the curves according to the non-dimensional values. So for this example, let's see, we've got our Reynolds number is 7 times 10 to the 6. The plot I'm showing down here, let me just blow this up a little bit. The plot I'm showing down here is a plot of average Nusselt number as a function of Reynolds number for an external flow over a flat isothermal plate. So this chart is specifically for this problem, right? We've pulled this chart based on the specifications that we just decided when we classified the problem. So all I do is I take my 7 times 10 to the 6, that's my Reynolds number. I'm going to find the corresponding spot here. So 7, 10 to the 6, this is a log plot, so that's going to be something like here. And I'm just going to start going up. Right? This is the line that I care about here. All right, the other piece of information I have is a Prandtl number. And the Prandtl number was 2.61, something like that? 2.69, 2.7. So these multiple curves that show up, these blue lines, it's a little hard to see, these all correspond to different Prandtl numbers. This solution has been plotted out for each of these Prandtl numbers. So there is one for 2, that's pretty close. So I'll maybe pick a number that's slightly above that 2, and closer to the 10, maybe it's right here. All right, and then I'm going to draw over to the left-hand side, and this is my answer. So the answer, the heat transfer coefficient, I guess in my notes I had it as roughly 1 times 10 to the 4th, but maybe it's 1.5 times 10 to the 4th, something like that. So in the end, I'm going to say my Nusselt number. Get this back. I'm going to say the Nusselt number, NU bar, this is my average Nusselt number, is equal to, I'll call it 1 times 10 to the 4th, just to be consistent with my notes. But it's something like 1.5. All right, so this is how you'd use the correlation. But the average Nusselt number is maybe, it's interesting, but it doesn't really answer the question, which is how much heat transfer is between the plate and the fluid. So now we need to take this and go back to our dimensional values. Okay, so there's always this relationship between heat transfer coefficient and Nusselt number, and it is the Nusselt number is equal to, let's say the average Nusselt number is equal to the average heat transfer coefficient times the characteristic length over the fluid's conductivity. So we already decided that the characteristic length for this problem is the length of the plate. Right, so L characteristic here, L characteristic here for this problem is just L. If it's like external flow over a cylinder or some other geometry, it would be the characteristic length for that geometry. But here it's L. Okay, so let's solve this for h bar, and then we can actually get the numeric value back. So h bar is equal to Nusselt bar times k over L. Plug in the values. Now we have 10 to the 4th times 0.66. That's our conductivity. And L was 1. And so this gives us 6,600 watts per meter squared Kelvin. All right, so this is giving us our dimensional value. Next step would be, I guess I've sort of run out of room here, but now we're going to plug all this in, right, to our heat transfer. We're ultimately asking for total heat transfer from the plate to the water, so that would be Q dot is equal to H bar times AS times T, S minus T infinity. We are given all that information, and we just computed H bar. So you evaluate this out, and for this example, it becomes 6,600 times 0.5 was the area, times 380 minus 300, and this equals 264,000 watts. All right, so that's the answer to the question that was originally asked for this problem. Questions on this? Yep.
When will we know if we should use that table as opposed to the equation?
I'm sorry, I didn't quite hear you.
When will we know if we're using that table to get the Nusselt number as opposed to using the equations in the table like this line up here?
Yeah, so like when would you know this particular table as opposed to the equations in the slide earlier? So what we have earlier is like usually models of boundary layer thickness. Like you have a general form of like a Nusselt number in terms of Reynolds and Prandtl. This is like a very specific set of correlations for this type of problem. So the way you generally know is if you can find a specific correlation for your problem that matches really well, you'd use that specific set. Right? So this table happens to exist. It's perfect for what we want, so we use this. If this doesn't exist, then you have to go to like, okay, your own experimental data, you have to go to an approximate model, you have to go to just something that looks kind of similar, that has similar characteristics, but it doesn't exactly match. And in all those like steps of removal, you're introducing uncertainty in your solution, basically. Good question. Yeah?
So the local value just only looks at a specific position on the plate, while the average takes into account the
Right, yep. The question was the local looks at specific location versus average takes everything into account. So yeah, what we're doing in this average here, right, this Nusselt in terms of L, it is the integrated Nusselt number, the integrated local Nusselt number from x equals 0 all the way up through x equals L, the end of the plate, including that transition from laminar to turbulent.